Hi, welcome here today. We've got a really exciting visitor and talk for you. Jason Ansel is visiting us from Meta, where he is a principal research scientist and technical lead for compilers on PyTorch. And so he'll be telling us about a bunch of the things that went into PyTorch 2's compilation to achieve faster ML models running. Jason also got his PhD at MIT, working with Saman Amarasinghe. Maybe I mispronounced that slightly. Probably close to
Close
right.
enough.
But anyway, he's a really great guy. I always appreciate running into him at conferences, and he was gracious enough to agree to come give us a talk about what's been going on. So without further ado, go ahead and take it away, Jason.
Wonderful. Thanks for having me. I'm excited to be here. And definitely feel free to interrupt if you have questions. Let's get started. So to set some context around PyTorch 2, there's been this thing that's been happening for a while called the Great ML Framework Debate, or at least that's what I call it. And that's this difference between eager mode frameworks and graph mode frameworks. And maybe it's first better to start with explaining what a graph mode framework is. And this is what like a lot of the early machine learning frameworks were, like Caffe2 or TensorFlow 1, where these frameworks, when you write code in those frameworks, so as you write like A plus B, what you're doing is you're defining a graph. And so A plus B constructs an addition node, and then you, after running lots of these nodes, you end up getting this graph object. And that's the graph object is the thing that you run and execute later on. So there's this layer of indirection when you run something. Similarly, or I guess in contrast, an eager mode framework, when you run A plus B, it just runs those two operations. So if you want to debug it, you can debug it in the way you'd debug a normal imperative program, like by using like print or a debugger like PDB. And there was a time, which we've now passed, where we saw this big split, where there was a number of machine learning frameworks that were eager mode, a number that were graph mode. And what we saw was that backend writers, framework builders, hardware developers really preferred these graph mode frameworks because they're easier to optimize. And users overwhelmingly preferred eager mode frameworks because they're more straightforward, they're easier to debug. And we saw over time that users gravitated to PyTorch. And one of the main reasons people gravitated to PyTorch is because of this eager mode programming model. And this eager mode programming model was so effective that when TensorFlow 2 came out, TensorFlow actually switched from a graph mode programming model to an eager mode programming model because of that better usability. But there are trade-offs to this. And because of the benefits of graph mode, because we want the performance impact, we want the easier to deploy and understand, PyTorch over the years made many different attempts at adding graph modes to PyTorch. And so the first of these was TorchJIT Trace, which was basically a record and replay system, where we recorded what operations your model did, and we just assumed that there was no control flow or any non-visible operations. The problem with this was it was unsound. It could give silently incorrect results. The next attempt we made was TorchJIT Script, which basically tried to ahead of time parse and re-implement Python. But Python is really complicated, and in practice, this only worked on around 45% of models. And there was this high effort where sometimes we'd hear people say they spent months torch scripting their model. And then the final other attempt was lazy tensors, which was started in the TorchXLA project, which captures gas graphs through deferred execution. And this maintains a lot of the usability, but it has a lot of performance and overhead problems. And so, what did we learn from all these different attempts at sort of trying to add graph mode-like things to PyTorch? Is we learned that PyTorch models are fundamentally not static graphs. Because PyTorch has the history of being this eager mode framework, where we give people the full power of Python, what we found is that people often used it. People would convert PyTorch tensors into other data formats, either native Python types or they'd call NumPy. We'd see third-party libraries in the middle of your forward method. People even do like more crazy stuff like construct classes, read files, do network requests, and all these basically broke the assumptions of these graph mode backends, where part of the problem that we were trying to do was we were putting a square peg in a round hole. And so one way to think about this trade-off is that there's this usability performance trade-off, where in one axis you have how usable a framework is, the other axis you have the performance, and before PyTorch 2, you really had this choice of the high usability of a framework like PyTorch, or one of these many existing graph mode frameworks where you often made large sacrifices to usability, and sometimes, although not always, got performance benefits. And so the goal of PyTorch 2 was really to get the best of both worlds. Like, how do we make something that goes fast, but also maintains this eager mode programming model that people really are drawn to PyTorch for? And so the main feature in PyTorch 2 is this feature called torch compile. And the contract is pretty simple. You pass in your model, and you get a model that goes faster. And there's many arguments to this. We have a mode argument, where you can say reduce overhead. If you have an overhead-bound model, this will increase memory usage, but lower fixed overheads. We also have a max auto-tune mode. This max auto-tune mode will do additional compile time optimizations, so it'll take longer to compile, but can produce faster results. And we also have a backend argument, where we make it really easy to define a custom backend for your model. And I'm going to talk about a backend called Inductor in this talk, but there's now more than 20 open source backends developed by the community for torch compile. And another argument here is dynamic equals true, which allows you to have better performance for dynamic shapes. And so you can avoid the need for padding and generate code that's robust to different sizes. And PyTorch 2 is fully backwards compatible to definition. You don't have to use to compile. It's entirely an opt-in feature. So for this talk, I'm going to start off by talking about Torch Dynamo, which is the graph capture mechanism inside of Torch Compile. After that, I'm going to talk about Torch Inductor, which is the default compiler backend for PyTorch. And then I have a final section where I'm going to talk about some more recent work on adding a Halide backend to Torch Inductor. So let's do an example about showing, basically, the point of this example is to show how easy it is to define a custom backend for PyTorch 2. So here, I've defined a function called myCompiler. And myCompiler takes in a graph, which is an FX graph module, and some example inputs. And for this example, my custom compiler, all it does is it prints out the graph that's been given for illustration purposes. But you could imagine implementing your own optimizing compiler inside of this function. Next, you have a decorator, torch.compile, and you can basically just pass your function in as the backend equals argument. And then I have a toy example here, which illustrates some control flow. And this is data-driven control flow. And so if I run this with Torch Compile, I get three graphs printed out. So the first graph is basically everything up to the if statement. The second graph is what happens if I take the true branch of the if statement. And the third graph is what happens when you take the false branch of the if statement. So basically what Torch Compile is doing is it's breaking up your program into possibly multiple graphs. And then those graphs are each passed to the backend compiler. And the key thing here is that all the complexity in Python, including data-driven control flow, but also things like third-party libraries, aren't passed to the backend compiler. So we run those using standard Python, and then we'll compile many different graph fragments to speed up your program. And so how does this work? The way this works is by extending the CPython interpreter. So CPython has an extension point called PEP523. And PEP523 is basically designed to allow people to define custom just-in-time compilers for Python. And so on the left here, we have what basically the default Python behavior for when you call a function in Python. So when you call your function foo, it's going to create a new PyFrame object, which basically represents the call in the CPython interpreter that has a pointer to the PyCode object, which is a singleton. And then there's this function deep in the source code for CPython called pyevalFrameDefault. And a valFrame default is basically the interpreter loop for Python. So it's actually going to operate, it's going to interpret the bytecode one bytecode at a time. And the way TorchDynamo modifies this is by intercepting at this by basically replacing this pyevalFrame default. And instead, what we do is the first time your function's called, we dynamically analyze the bytecode of your function. And the goal here is to basically split the things out into two pieces. So we split the bytecode into a graph of PyTorch operations, which is the FX graph we have, and then any Python bytecodes, which is possibly none, which we couldn't transform, we just leave as regular Python bytecode, and we pass it to the standard Python bytecode interpreter. And then the great thing about this is it gives us basically full support for all of Python by default, because if we do nothing in this transformation, we just take your original function, convert it to the same exact bytecode, and then interpret it. And so it's really easy to support complex Python behavior in this model, and it allows us to sort of incrementally only optimize the things which is supported by our backend compilers. And because this analysis is expensive, we need to cache it. And the way we cache it is by any runtime properties which we've specialized on, like, for example, the types of the arguments. We insert dynamic checks, which we call guards, and we'll only reuse this cache if the guards pass. So let's go back to this toy example. So here we have the function that I showed earlier. And so when toy example is called, TorchDynamo takes control in this custom evalFrame function. And this custom evalFrame function takes in flocals, which is the arguments to the function, in this case a and b, which are both tensors. It has a pointer of the globals, which is basically the module scope of this function. And then in the frame, we also have the F code. And this F code is the bytecode of the function. And so here's the bytecode that you get from this toy example. I'm not expecting you to understand everything about this bytecode, but the way this works is on the left we have the memory offset, in the middle we have the instruction, and then the right side we have the arguments, the argument to the instruction. And Python bytecode is basically a stack-based virtual machine. So every operation is going to pop some number of operations off the stack, and then push some number of outputs onto the stack. And what TorchDynamo is going to do is it's going to analyze this bytecode one instruction at a time. So let's walk through what this analysis looks like. So to start off the analysis, we have the bytecode in the middle, and we're going to start on the start first instruction. And we do some setup to begin with. So we have the symbolic locals on the left, where we basically introduce what we call a variable tracker to track the state of both the local variables of the function, and which is in the top, and then also the stack, which starts off as empty. And the right, we have the FX graph that we're going to produce. And so here it starts off with placeholder A, placeholder B, which represent the two arguments to the graph, and which are just the same as the arguments to the function. And so let's go through the symbolic analysis. So looking first at the load fast, what load fast will do is it'll take the symbolic local A and it'll push it onto the stack. Next, we have load global torch, which again will reach into global scope and push the global onto the stack. We can note here that every variable tracker here has some guards associated with it. So we are keeping track of both the value, which is a pointer to a node in the graph, then the source, basically where it came from, which we use for code gen, then also the guards, which is basically like what do we need, what invariants do we need to check in order for this transformation to be reused. Next up, we have load method. So load method is going to pop the torch object off the stack, and then read torch.abs from torch, and push the results of that onto the stack. In this case, we can keep the same guards as the function match torch guard, because we know that torch.abs is something that's owned by PyTorch, and so we only need to guard on the fact that the global variable torch still points to torch. We don't need to guard on torch.abs. Next, we load fast A, which is the argument to torch.abs. Finally, we hit call method, and call method is going to take these 3 objects on the stack. It's going to pop them off the stack. It's going to add a new function to the graph. So in this case, we've captured a call to torch.abs in the output graph we've generated. And then finally, it's going to push the result onto the stack. And the result here now has the proxy on the result points to the node in the graph that we've tracked. And the guards are the union of all the guards of the inputs. So hopefully you get a sense for how we process this bytecode. So I'm going to sort of fast forward all the way down to this pop jump if false. Because this pop jump if false, so now control flow is an interesting case. In most cases in PyTorch, we're able to statically determine which branch we're going to take in control flow, because most models don't have dynamic control flow. But this specific example has dynamic control flow, so we don't know which direction this pop jump if false will go. So this pop jump if false will either continue on to the next instruction on line 30, or it'll jump to offset 38. And we don't know which one. And so what we're going to do is, rather than trying to do some sort of complex analysis where we try to analyze both sides of the branch, we simply say, okay, we're going to stop our analysis here. We're going to compile the graph we've collected so far, and then we'll recursively continue the analysis once we've figured out which side of the branch we're going to take. And so now how do we stop this analysis, and how do we basically compile the output of code? Well, first we need to look at all the live variables. In this case, we have 3 live variables, and 2 of those live variables are coming from the graph. So we need to add an output node to the graph, which returns the 2 live variables that we need. We also need to collect all the guards together to basically say, okay, what needs to be checked for this thing to be valid? In this case, we have a guard on the 2 arguments. They're both tensors. And then also the global variable torch needs to not have changed, because in Python, you're allowed to say, torch equals numpy, and your program will continue where every time you say torch, it'll say numpy. And so we need to check for that, for this to be valid. And from all this, we then generate this output bytecode. And you don't need to understand all this output bytecode, but basically what this bytecode has is 2 main parts. And so the first part is to call the compiled graph. So we basically took this fx graph that we accumulated on the right. We called the compiler, in which case this was the myCompiler function that I showed previously. And we need to call that. So we have here, we're going to load the results of the compiler here, which is compiled function 0. Then there's some boilerplate code, which I've highlighted in the 2 boxes, to collect the arguments to the graph. And then after we call the compiled function, we also need to unpack the arguments. So one of the outputs of the graph belongs in the local variable x, which you can see here, and then the other belongs on the stack. And we put everything in the right place. And then the remainder of then we have the pop jump if false on offset 12. So we basically just take the bytecode that we stopped at, and we just copied and pasted into the output function. And then we generate 2 what we call continuation functions. And these continuation functions are resume at 30 and resume at 38. And the way that these continuation functions work is we take the original bytecode of the function, we just copy it into a new function, and we put a jump absolute at the top. So resume at 30 is jump absolute offset 30, followed by the original bytecode of the function. And then similarly, resume at 38 does the same thing, but for offset 38. And the key part here is that by structuring the continuation code as a new function, we're actually going to recursively invoke Dynamo. So whenever we call a function, our eval frame hook takes over. And so if we take the true branch, the very first time we call that true branch, all this process is going to start over, and we're going to analyze the rest of this function as if it were a brand new function. This allows us to basically continue our analysis without writing any additional code. So this was a pretty simple example. And Torch Dynamo supports a lot of other complex things. I won't go into these, but basically there's large parts of Python's behavior which it models symbolically. So if you have something like a list or a dictionary, it'll symbolically model all your dictionary operations. And if your dictionary never escapes your function, Torch Dynamo is actually going to compile it away, where your resulting code won't even use the dictionary, so it'll go faster. But if you take one of these data structures and return it outside of the Dynamo compiled region, Torch Dynamo is going to still generate a graph, but then at the very end, after the graph runs, it's going to reconstruct all of the needed state that would have happened. And this includes mutations. So if you do something like in the middle of your function, you write to a global variable and you mutate that global variable, we'll process through that, and then we basically generate an epilogue that runs after the graph that's going to replay all of the side effects that your program would have. OK. So there's another piece which I skipped over, which is AOT Autograd. AOT Autograd basically allows us to support training. And I'd say if you're planning on adding a backend to PyTorch, you should definitely look into AOT Autograd, because that allows you to take the forwards graph, which I just talked about, and turn it into both a forwards graph and a backwards graph, and also do IR normalization. But the main thing I want to talk about next is Torch Inductor. Oh, yes.
I was curious if I'm calling, say, into some gigantic, completely machine learning unrelated function, just to be perverse, in the middle of this, does that just get retained as such, including all of its mutative effects? Can all those just be delayed, or is there some limitation on what can be interpreted in this way?
So a lot of side effects can be delayed. So like, for something like, if you construct a class in Dynamo, what we'll do is we'll actually like track the fact that, oh, you constructed a class, you set all these attributes on the class, and then if you never actually return the class, we actually never need to, we can actually just skip constructing the class. But
I just start doing arbitrary back and forth, not just setting, but reading global state.
Yeah, so when you read global state, we first check, are there any pending mutations to that global state? If there's a pending mutation to that global state, then we'll
system calls then? Or?
Yeah, so if you do something that we don't support, like for example, you make a syscall, okay, where then we do this graph break thing that I just talked about, where we'll stop the analysis, we'll generate a function that runs everything up to that syscall, and then we'll then run the syscall for real, and then we'll recursively start over right after the syscall.
Okay.
Yeah.
Got
it. So if there's literally no PyTorch code in your program, then this could be this will just add overhead because we're not actually compiling anything. So there are some heuristics to try to detect that, where we look at all your local variables, and if none of them are tensors, and you're not like there's no references to PyTorch functions later on, then we actually just like bail out and we just say like, okay, we're going to skip this frame. But in general, this should work for arbitrary thing. All right. So what's Torch Inductor? So I mentioned before that there's around 20 backends that are developed by the open source community, but we wanted a PyTorch native backend that's basically the default backend for Torch Compile. And to start off with, like, what are the main principles that motivated our design? So first, we wanted something that was PyTorch native. So PyTorch has a lot of abstractions, which are pretty unique to it. One is user-visible strides and memory layouts and views and aliasing and mutation. And we wanted a compiler that sort of shared similar abstractions. Second, we wanted something Python first. So we actually implemented Torch Inductor entirely in Python. And the real motivation here is to make something that's hackable by users. Like most machine learning users are much more comfortable in Python than C++. And we see that in community contributions to PyTorch, where the Python parts of PyTorch get far more community contribution than the C++ parts. And then finally, we want something breadth first. And so we focused really early on supporting all the weird stuff in PyTorch because we wanted to compile a design that could scale. Next up are the three key technologies. We have a defined by run loop level AR, which basically means that the body of a loop, basically the element-wise code that the operations is actually defined by a Python function, which is a pretty unique way of designing a compiler. Second, we really wanted sort of support for dynamic shapes and strides built in. And so we use SymPy to reason symbolically about dynamic shapes. And then finally, we wanted to reuse state-of-the-art languages. And so we looked around at what people were writing custom kernels in that was really hitting state-of-the-art performance. And what we saw is that Triton is increasingly becoming the language for writing custom kernels on GPUs, and C++ OpenMP for CPUs. And so we actually generate human-readable code as an output of our compiler, which makes it easier to understand exactly what the compiler is doing. So what is Triton, if you haven't heard of Triton? So Triton is a DSL for programming originally GPUs, but now also many other types of AI accelerators. The way to think about it is it's higher level than CUDA, but it's lower level than a lot of existing DSLs. And it really sort of strikes a right balance where it makes it easy to write high performance code for GPU systems. So here's an overview of how Torch Inductor works. So first we have AOT Autograd. AOT Autograd captures the forwards and backwards graph, and it fundamentally adds training support. So if we didn't have AOT Autograd, we wouldn't support training. It also simultaneously, while it does that, it also does decompositions to a smaller operator set. So PyTorch has around 2,000 operators total, but after we've run through the decompositions that happen in AOT Autograd, we're down to around 200 operators. Then it also does functionalization. So we take any mutation and we rewrite the graph to not use mutation. Next, we have inductor graph lowering. So inductor graph lowerings take this around 200 operator set and converts to Torch Inductor's loop level IR. So we've gone from an IR that's operating on tensors to an IR that's operating on scalars. And at this point, we've further simplified the IR to now around 50 operators. Next up, we have scheduling. So scheduling is where we decide, OK, what gets fused with what. We make tiling decisions and memory planning and stuff like that. And then finally, we have our code gen. And so we have our wrapper code gen, which outputs the code that calls the kernels, which replaces the interpreter. We either generate Python for this or C++. We have two different modes. And then we have backend code gen. So for backend code gen, we have either Triton or C++. And actually, very recently, we added Halide, which I'll talk about at the end. And so let's walk through an example of what this compilation process looks like. So I have a new toy example here where we're calling sine and cosine. I basically run this example with a specific tensor, and I'm getting a lot of this information that I'm going to show in the next few slides by running with torch compile debug equals 1 on the command line. So after running the AOT autograd lowering, I get this A10FX graph. And so for this example, for simplicity, I'm only showing the forwards graph. But if we were doing training, we'd, in addition to the forwards graph, also have a backwards graph. At this point, we now have types in all the intermediates, and we've actually narrowed down the specific implementations to torch.ops.a10. So we've basically, like there's many overloads to a lot of the operators. We've resolved these overloads. We've simplified the IR down to a smaller operator set. Next up, we lower this to the defined by run IR that I talked about before, where the IR for each of these ops actually consists of a Python function which we generate programmatically. And so this is what the Python function would look like if you actually wrote it out. But in practice, it's actually like a series of closures that's generated. So we have the first function, which takes an index. And then from that index, it calls ops.load on a specific memory address of arg1, which is a buffer. It then calls ops.sign on a temporary and returns the result. And then on the right side, we have the metadata associated with these, which basically says, like, OK, what are the sizes? What are the D types? And so on. And so this choice of a defined by run IR makes it very easy to construct these type of operations because there's basically no boilerplate involved. And so for us, like one of the biggest challenges of writing a compiler for PyTorch was dealing with how many operators PyTorch has, and some of these operators are very complex. And so by using a define by runIR, it actually makes it really easy to construct this. Later on in the compilation process, we actually lower this define by runIR down to a graph, so we can actually manipulate the individual operations. But at construction time, we use this define by run pattern. Next up is scheduling in Fusion. On the right here, I'm showing the graph that we've captured in the sort of the scheduling thing, where we have the two operations in red, and then the input and output on the top and the bottom. And the sort of key functions that control this process is first can fuse, which basically checks, okay, given two nodes in the IR, can we fuse them into a single operation? We can either fuse operations horizontally, so basically two operations which read the same data but write separate outputs, or vertically, where if we have like a producer-consumer relationship and we want to fuse things together that way. And then there's also score fusion, and score fusion basically decides the order that we fuse things in. And so because some fusions are mutually exclusive, like fusing two operations, fusing A and B can prevent you from fusing B and C. The score fusion is important to prioritize which fusions we do. And we basically just run a greedy algorithm to deciding what we can fuse. This is also something where fusions can open up new fusion opportunities, and so we repeat this process to a fixed point. So here's the output Triton code that we generate. So if you're not familiar with Triton code, Triton operates on fixed size blocks. So in this case, what we do is we are loading a block of XBlock elements all simultaneously. And then we're calling sine and cosine on this block of elements we've written, and then we have the two stores of blocks of elements to the outputs. And you can see that in our output code, we've taken these two separate operations, we've fused them into a single kernel for the output. And then here's what the wrapper code looks like. So the wrapper code is the stuff that calls the kernels. It also does memory allocations. So you can see some stuff here for dealing with shapes, so like passing the symbolic shapes around, and then also doing the memory allocations, then calling the actual Triton kernel. And if you're curious, here's what the C++ generated code looks like. So if I move the tensor to C++, instead Torch Inductor will generate this code, where what we have is we have an OpenMP parallel for loop, and in that parallel for loop, we're calling this class ATVec vectorized. And so basically, this is a C++ class in the PyTorch source code. This is how eager mode kernels are written in PyTorch in a vectorized way, and it allows us to generate vectorized output code. And so how does this work? So here's some performance results. These performance results are actually a little bit stale. These are from our paper in ASPLOS at the beginning of the year. But we've improved quite a bit since then. But basically what we have speed ups. So basically 1x in this case means you're running the same speed as PyTorch eager. We have inference in blue, training in red. And we're comparing to 6 other compilers. And we can see that, and then we have these 3 benchmark suites. So TorchBench is a benchmark suite consisting of 57 models. And those models, or it's actually grown since then, but at the time it was 57 models. These models are basically primarily research models. So what we did is we went to papers with code. We looked at very highly cited papers, and we took the models that those papers were based on, and we turned them into benchmarks. Next, we have Hugging Face models. So Hugging Face is primarily transformer models. And it's a very popular repository. We have for this we have 45 models from Hugging Face, and then we have 60 models from TIM, and TIM is a popular vision library. So you have a lot of like convolutional type models there, and we can see that basically across all of these, Torch Inductor is generating significantly faster code than the other compilers we measured. in the paper, we also have a lot of graphs that look like this, and which is I love this way of looking at the performance results. So in this case, we have a cumulative distribution function. So we're looking at, okay, how many models were faster than a certain speed up. So here you can see, right in the middle, you have the 5x line. So it says speed up greater than, and you can, if you look at that, so approximately for torch inductor, approximately 25 models got a speed up larger than 5x. And as you sort of change the speed up, you can basically see what's the distribution of speed ups that we're seeing. And you can see that there's a pretty large number of models where torch inductor is generating large speed ups in excess of 4x. Well, that's not true for basically any of the other compiler backends. As you look closer to look down to smaller speedups, you can see that XLA sort of starts standing out here, where XLA is generating some speedups, in the 4x to 1x range for lots of models. Although overall, if you take the geomean, XLA actually isn't number 2 because those speedups are offset by slowdowns in other models. Then around sort of the 1x line, you'll see NVFuser and NNC. NVFuser and NNC both have speedups that are sort of clustered around 1x. And the reason for that is they actually reuse a lot of eager mode PyTorch kernels. So they're only compiling part of the model, not the entire model. And then for TVM, Onyx, and Hidet, where TVM and Hidet are research compilers and Onyx is an inference framework, we're primarily seeing slowdowns there. So there's very few models where those are faster than PyTorch Eager. So here's a breakdown of, okay, yes?
Slides ago, can you say a bit about the gap between the improvement for inference versus training? Like, do you know why there's a gap there?
Yeah, that's actually to be expected because basically the short answer is inference is a lot easier of a compiler problem than training. And so when you have a inference graph, most inference graphs basically look like a line where you have like layer feeding into layer, feeding into layer, feeding into layer. And basically the way you want to compile that line is you just want to fuse as much as you can. And you see like pretty big speedups because every time you fuse something, you basically eliminate two memory accesses. You eliminate the store, then you eliminate the load. While for training graphs, you still have that same line, but along the way, you need to save what we call activations for backwards, because basically you need to know the gradients of all these operations. And so you have that same line, but now you have all these spokes coming off the line for that stuff you need to save for the backwards. Then you have basically the same graph in reverse, where you're going the opposite direction through it, and you're basically consuming all those activations in the opposite order you have. And so if you think about a fusion in training, you still fuse the two things together, but now you still need to save that activation for backwards. So rather than eliminating two memory accesses, the store and the load, that same fusion only eliminates one memory access. It eliminates the load, but you still need to do the store. And so there's basically just this, like from a compiler standpoint, makes it a much more interesting problem because there's now choices in the graph. Like all of a sudden, oh, you could either do this or you could do this. You could move stuff between forwards and backwards. It's a much more interesting compiler problem, but it also has less speedups because you basically have to save all these activations.
The other question I had is, so nowadays, like, there's a lot of these like inference engines that have like custom kernels for like LLM inference mainly, I guess. Do you have any idea like how it would compare to the improvements here?
Yeah, we've compared against a lot of inference engines, and what you end up getting is you end up getting like a pretty large overfitting effect with a lot of these, where like on specific models which people have spent a lot of time on, they get like they can do a really good job. Where basically like if you highly optimize like BERT, and then you pass BERT to your inference engine, the inference engine might say like, oh, I see that you're compiling BERT. I'm gonna swap out a huge chunk of your model for this handwritten custom kernel. And so you see like these cases where on specific models, you get really incredible performance on a lot of these engines. But then if you run on like a large number of models, like on our paper, we're measuring on 180 distinct models. what you see is that like the average performance is actually pretty low because you have these pretty high performance cliffs where like if it's the thing that the inference engine is optimized for, it does great, and then if you pass it something a little bit weird or you change the thing just a little bit, often you see a big performance cliff.
Thanks.
Yes, but like I guess on average across like 180 model type systems, our data shows that we're ahead. But on a specific model, it really depends, and often we're not the best on every model. We're best on average.
I wonder like how Torch compile handles like different kinds of parallelism and like model parallelism, data parallelism, and how like for this parallelism you also have like communications, collective communications in between. So how does Torch compile handles such situations?
Yeah, so in PyTorch, the distributed stuff all happens in the framework, in the layer above it. So we have a system called DDP for data parallelism, FSDP for sharded parallelism. We also have stuff for pipeline parallelism and model parallelism. And basically all those exist as sort of a layer above PyTorch, where the way that you distribute your model is defined by sort of the framework above PyTorch that you use. And what happens for those is the compiler understands those things. So we'll take the collectives and we'll compile them. But for the most part, we're just taking the collectives and we're emitting them unmodified to the output graph. So in the latest stuff, there's some work to do some like collective communication optimizations. But basically, all these numbers are single node numbers. And when we're doing distributed stuff, we're basically optimizing. The way we're doing is we're optimizing the local compute to try to like reduce the compute intensity of the kernels, and then we're relying on whatever distributed framework the user is using to basically define, okay, where should you do an all reduce, where you should do the like what collectives you should use, and so we support compiling collectives. In the very latest version, we support some optimization of collectives, but the parallelism strategy, like okay, like are you going to do pipeline parallelism, is defined basically by either by the user or by the distributed framework. Okay. This is a breakdown of basically where the speedups are coming from, and so this is an ablation study. So basically what we've done is we've taken Torch Inductor and we've one by one started disabling optimizations. And so, for example, without mapmul templates so basically for matrix multiplies, we have templates for that map it to Triton and can do epilogue fusion. And if you turn all that off, you can see that things get 0.6x slower in inference and 0.4x slower in training. And so that can sort of give you an idea of, okay, how important is that optimization? And there's lots of optimizations listed here. They're all described in the paper. But the one thing to take away here is that the two biggest ones by far are fusion and inlining. And those are so important that I had this last line where we disable them both. And if you disable them both, you can see that we're actually even slower than one. So basically, we were slower than eager mode. And the reason for that is that we decompose operations into smaller units. And if you decompose, for example, a softmax into its constituent operations, in order to actually get back to 1x, you actually have to fuse stuff together. And so this sort of fusion and inlining is basically the primary source of our speedups, although we do see speedups from other places. Yep.
Or should I understand each of these as here's the system with all optimizations, and each line is just removing that one optimization?
Exactly.
Okay, so it's not a stack up of multiple of
this is not cumulative. This is like all optimizations but one, except for the last one where I turn off two optimizations.
Sure, yeah. Do you have, do you know anywhere else there's significant interactions between them, or?
I think the biggest interaction is inlining. There definitely are other interactions, and like I think a lot of these things have pretty complex interactions where okay, the cost of multiple kernels is affected by CUDA graphs. The pattern matching stuff changes what the operations you have, and so like they're highly interdependent. But this is in some sense, it's really hard to do this attribution because of how interdependent it is. But I think this sort of like ablation study type thing is a decent way of estimating it. All right. So in the last few minutes, I'm going to talk about some more recent work. And so a few months ago, I added a halide backend to PyTorch 2, specifically to Torch Inductor. And so, I guess the first question to ask is, okay, like why add a halide backend? And really, the primary focus of the halide backend is as a reference backend intended to help other people extend Torch Inductor. And so like a really common question that I get talking to startups and talking to other companies is, the people are like, I have my custom hardware, how do I make it work with PyTorch? Or I have my new cool research compiler that's trying out new ideas, how do I make it work with PyTorch? And so we have a lot of extension points in PyTorch. We have this extension point that I mentioned earlier, right below Torch Dynamo, where you get sort of this graph of A10 operations that's operating at the high level. You can also extend PyTorch by adding a backend to Triton, and so like a number of projects, including AMD and Intel GPUs, have added their own backends to Torch Inductor, and so you can basically use backends to Triton, and so you can basically extend Triton. But there's some cases where you want something in between. You want something that's lower level than an A10 graph, but higher level than Triton. And I thought, and so basically you can add a backend to Torch Inductor. So basically, rather than having Torch Inductor generate Triton, instead you can generate halide. And the nice thing about halide is it's one of those compiler projects that's inspired a lot of other projects. And so there's many sort of direct forks of halide like TVM. There's also lots of compiler projects that were inspired by halide, including NVFuser and NNC, which I talked about earlier. This basically forces a lot of generality into Torch Inductor and allows us to basically point people who want to extend PyTorch at this backend as a good starting place for adding a new Torch Inductor backend. Sort of that middle extension point. So I want to compare the lowering stack a little bit to sort of the most obvious comparison, which is TVM. And so for this halide backend, we start out Torch Dynamo. We go through Torch Inductor, which supports both training and inference and supports about 95% of models, according to our benchmark suite. And then it maps to halide at the bottom. In contrast, the TVM backend first goes through TorchScript, and then it goes to TVM's intermediate language, which is Relay or Relax. It only supports inference, and empirically it works on about half of models. And then it goes to the TVM backend. So what's the current status? So this is basically complete from a sort of a functionality standpoint. So most tests and models run correctly. The early results, which I'll show a little bit later, are slower on average. But I think the big lesson from this is automatically creating, and basically the way we're generating the schedules for this is we're using the halide autoschedulers. There's, I think, 5 autoschedulers built into halide, and we're using those. But what we found is generating halide schedules is really hard. And this is actually a little bit funny because I was automatically generating halide schedules back in grad school, 10 or 15 years ago. And it was hard back then, and it's still hard today. And so let's look at sort of an example to illustrate that. So here's an example code that you get by calling torch.sum. And this is the generated Triton code. You can see you have a block, you loop over the blocks, and then you finally do an accumulation at the end. And if I run this on my local GPU, it takes about 1/3 of a millisecond to run. Then if I take the same example and look at halide, this is the generated halide code. Arguably, the code's actually a lot simpler. Like we don't have that sort of loop embedded into it. It's cleaner code. The problem is if I run it with the autoscheduler, it's more than 4x slower than the equivalent Triton code. And so we went to the Halide devs and we asked them, how can we make this faster? And after a lot of back and forth, about a month later, we had a handwritten schedule for this example. And this handwritten schedule sort of gets within 10% of Triton. So it's still a little bit slower, but with sort of like a heroic amount of human effort, you can get pretty close to Triton, but not quite as good. So it shows that there's clearly a lot of room for improvement, at least on the GPU performance. So let's look at some other things. So this is some performance on Torchbench models, where we're basically here showing the distribution of speedups. And I'm showing the distribution because if I take the geomean, a lot of the examples are like 100x slower, and so the geomean would basically just be 0. But basically what we have is red means it's not working. Most of the not working things are basic errors in the autoschedulers. Yellow means that Halide is slower than eager mode. Blue means that Halide is faster than eager mode but slower than Triton or C++. And then green means that Halide is actually generating a speed up. So we can see that on the NVIDIA A100, there's only a few models, which are pretty weird models, that Halide is generating a speed up. And then similarly, we see the same thing on the bottom two, which are the x86 CPUs. But actually on AMD, when we ran these numbers, we actually saw that Halide was actually doing really well on AMD. Sorry, ARM, not AMD, my mistake. And I think what this pointed out was that actually like we hadn't done a great job optimizing our ARM performance. And this actually caused us to go, and since I generated these numbers, go and actually fix a bunch of issues where we actually weren't vectorizing ARM code properly. But it does show that, like, especially on more exotic architectures, having multiple backends can be a good way to sort of check yourself, because you can see that, like, there's a clear gap here and there's room for improvements. And so I think we're using some examples here to try to improve Halide, and we're also using some of the Halide results to improve our other backends. And so with that, those are all the slides I have, and I'm happy to take more questions. I will call out some links to some interesting stuff. We have a bunch of content on our YouTube from PyTorch conference and some live Q&A sessions. I'd also really call out the PyTorch Dev podcast by Ed Young. This is a fantastic podcast if you want to learn more about the internals of how PyTorch works. And also I'll mention we're hiring, and you can reach out to me either for internships full-time or if you're interested in collaborating on research.
Question.
Do you know how this interacts with systems like PyTorch's like ExecuTorch or the quantization frameworks and backends?
Yes, so ExecuTorch and Torch.export, which ExecuTorch uses, uses Torch Dynamo. So basically the way it's capturing the program is to run Torch Dynamo. But then rather than compiling the results, ExecuTorch is basically an interpreter. So it takes the graph that Torch Dynamo captures, and then it just runs that graph using a lightweight interpreter op by op. So it runs basically the same kernels that eager mode is going to run. So it's not going to generate things any faster. So the goal is not speedups with ExecuTorch. The goal is basically to deploy to edge devices. So if you want to run your model on a phone, if you want to run your model inside your VR glasses or your VR headset, basically ExecuTorch is a way to package your model in a way that has very few dependencies. It reuses the first half of what I talked about here, but it doesn't. It's not going to make your model go faster.
And then with quantization, like current PyTorch quantization backends, like Hewitt and Packer, anything like that, do you know if it's compatible?
Yes, there are. Most quantization backends work with Torch Compile. There's actually like a number of different integrations with them. I'm not sure about that specific one, but we support at least 4 different quantization backends. Yeah.
So on your relation slide under inference, I think there was a line that was saying that disabling basically loop reordering and layout changes made almost no difference in performance. Did I read that right?
I believe that was only for inference. So you see here, 17 in training and 0 for inference. And basically, the reason for that is that a lot of the benefits we're getting from the loop reordering are materialized in the backwards. And because in the backwards, you end up having different communication, basically different communication patterns. Basically, what it is that the default eager mode layouts and loop orders work pretty well for inference.
I see. So this doesn't mean, for instance, that like gem is not like packing one of the matrices.
So specifically, this is loop and layout reordering for non-gems or for inputs to gems. So like so we're not for gems, we have a template-based approach. So we basically have like a gem. So that it's that line after it, the matmul templates. Basically, we have a gem template written in Triton with basically a spot for epilogue fusion. And we're not using this sort of approach for gems, because gems are the type of thing where like it's pretty. It takes a lot of work to actually get like a really fast gem, and so we're actually we have basically like a multi backend approach to gems. So we have cuBLAS gems, cuDNN gems, we have Cutlass gems, and then we also have Triton gems. And what you find is that for some shapes, Triton is fastest. For other shapes, Cutlass is fastest. For other shapes, cuBLAS is fastest. And these frameworks are all constantly improving. And so like they often like it's like a horse race where like one pulls ahead and then the other pulls ahead. And it's really hard to predict, OK, what's the fastest gem framework? And so what we do is we just, and this, you have to turn on like mode equals max autotune to get this. But if you do mode equals max autotune, what we do is we just run all the backends. We just measure them for your specific shape, and we just pick whichever one's fastest. And that sort of allows us to have faster gems than any one framework alone. And so that's our sort of gem strategy.
Kind of a follow-up on that. How long does your auto-tuning take? I worked on TVM, and like TVM's auto-tuning takes like a horrible amount of time. So I'm just curious, like, how that works in PyTorch.
Yeah, so we're not doing anything close to TVM style auto tuning. So our auto tuning typically takes seconds, and the reason why TVM auto tuning, actually, it's even worse than ours. Like I've run the TVM auto tuner for like a full week, and after running the auto tuner for a full week, I was like, oh man, this is going to be so fast, and I ran it. And it was worse than the default schedule. Like I'm like, okay, well, what did you do in this week? Where if you had just taken the default configuration, you would have like it was slower where it started. It was so frustrating. But yeah, I mean for us, like basically like our search spaces are just orders of magnitude smaller. So like TVM search spaces are these like are enormous. They're exponential. They represent sort of a lot of stuff. For us, when we're auto tuning, reductions or pointwise things, our search space size is 4. We try 4 things and we pick the best. For gems, our search space size is like 15. We try 15 things and then we pick the best. And so the cost of auto tuning is very teeny because we have these very targeted search spaces.
So maybe to pick on your Halide results, did you try running image processing pipelines through PyTorch? Because presumably the auto tuners for Halide are really built for those workloads rather than the ML workloads.
Yeah, they're definitely like, and a lot of the bugs that we were seeing where like the auto schedulers in Halide would just like crash or generate invalid code were, I think, image processing optimizations, which is played really poorly with PyTorch. So I think it's definitely the case where we're taking something that wasn't really designed for it and applying it to a new use case, and it's a fair thing. But
it does as well as it does.
It is, and I haven't tried running image processing workloads on PyTorch, but
maybe I'll suggest it to Andrew in case he's got a chip on his shoulder.
yeah. Andrew was involved in some of this stuff, and we're still not done. So like the follow-up work to the Halide stuff is like go make a competent autoscheduler for machine learning workloads. And so like there's actually like Andrew has like one of the new people on his team who's working on that, and so yes, it's Alex.
Okay. Cool.
so Alex is helping out to try to fix this, and so hopefully we'll see some better halide results in the future.
For the cases where there was like some hand-optimized model that did better than Torch compile, do you have any insight into like what kinds of things they're doing that, yeah, or maybe Torch compile is not doing right now? Like, do you want to support those kinds of things in the future?
Yeah, it depends. Like a lot of the big ones are things that we actually like have fixed. So like, so like one awesome thing we often see is basically just like custom flash attention or custom attention kernels. And so basically what there's been a lot of advancement in like the handwritten kernel space of basically finding basically just like highly optimized attention kernels that do play lots of tricks, which as far as I know, no compilers are really able to generate automatically. And so we do have passes, which this came after I generated this number, so the numbers might different, where we'll identify attention patterns and swap in attention kernel, like handwritten attention kernels. There's stuff like that. There's some cases where there's sort of like algorithmic tricks, but it depends. Like I think a lot of those gaps are things that we like fix when we find them, but I don't know.
Let's go ahead and give Jason another round of applause here. If you've got some more questions, please come up afterwards.
Yeah, thank you so much.